is powering the next generation data platform, Lalamove's streaming Lakehouse journey. I will co-present this material with my colleague Owen Ip. We have structured our session into 3 parts. And in the first session, we are going to briefly introduce Lalamove. And secondly, we will introduce the 3 scenarios that we met in our daily analytic life and how we use streaming Lakehouse to handle it. And in the third part, we will introduce how we governance our Lakehouse and how we ensure the stability and reliability of our Lakehouse. So let's start with part 1. And I'm going to introduce Lalamove. Lalamove is a 24/7 on-demand delivering platform, and it was founded in Hong Kong in 2013, and it covered 40 markets and over 400 cities globally, including Asia, South America, and EMEA. Lalamove was born with a mission to empower our local communities by making our deliveries fast, simple, and affordable. Individuals, small business, and corporations can access a wide fleet of delivery vehicles operated by our professional driver partners. And Lalamove has become the world's largest logistic transaction platform with 1.7 million monthly active driver partners and 16.7 million active users. And next, I will introduce our streaming Lakehouse journey. And we will introduce 3 scenarios that we met in Lalamove. And firstly, I will introduce how we tackle modern observability challenge and about how we untangle the complexity of chase data to resolve the microservices analysis. So what is chase? In our modern distributed system, a request can trigger a chain of microservices, making it difficult to know what is happening inside. A chase is an entire end-to-end request journey, showing the microservices it touches and giving you the clear map of what is happening within a request. So why need a chase analytic? With chase analytic, we can pinpoint bottlenecks, we can find out why our request is slow, and we can prioritize our applications, especially when there's something, incident happens, we could differentiate the systems and focus on the systems that is important. And we can also optimize performance according to the chase matrix. And last but not least, we can visualize the dependencies between the microservices and check if the traffic is reasonable or if there's any inefficient traffic between the microservices. So in short, microservices analytic help us to govern our microservices in a real data-driven way. So this is a typical requirement in our chase analysis, means chase topology analysis. As you can see from the graph, the endpoint get order info may be called by different scenarios and different microservice, like create order or complete order, and it may cause different issues, like slow request and error request. So in this chase topology analysis, the requirement is to identify the slow request and error request, and most importantly, to build up the lineage between the microservices and identify the route for different scenarios. And instead of using purely Flink to do this complicated computing, we utilize partial update and aggregation in Paimon to do this graph-like computing. And we have divided this computing into two stages. In the first stage, we focus on building the lineage of a chase, and we try to merge the parent-child relationship within a chase ID, and we customize merge map with a partial update mode to implement these functionalities. And the outcome of the first table is each record per chase that reconstructed dependency map. And in the second part, we unflatten the chase and unflatten the map, and we use the standard aggregation functions, and we pinpoint the bottleneck of the microservices, and we do the calculation with the aggregation function provided by Paimon. And I will introduce how and why we need to implement and customize this merge map aggregation with partial update. And chase is a complicated and disconnected data. And each of the Kafka message we receive is actually a segment. A segment is represent a single microservice. And segment contains a lot of span, and each of the span is kind of like a local master core or a database query. So if we need to build up the relationship of a chase, we need to merge the parent-child segments into a map. But how to link up the caller and callee? As you can see from the graph, the caller endpoint comes from the last span of the parent segment, while the callee endpoint comes from the first span of the first segment of the child segment. So we can't just overwrite the value. We need to join the caller and callee within the map, and we need to add more links into a growing map. And that's why we implemented the merge map in a partial update mode. And currently, Paimon, the standard function merge map in Paimon doesn't support partial update. So we implemented in our own, and this customized function has empowered us to build up the relationship between the segments and between the microservices. And we have seen how we resolve a data challenge in our observability. And now let's turn our attention to critical but a traditional task, data migration. When you think about data migration, what comes to your mind? A source database, a target database, or a temporary buffer like Kafka. Kafka is often hard to maintain, and sometimes the data will be lost after the retention period, and it's not queryable. So we have reconsidered the data migration model. What if we change the Kafka, the temporary buffer, to a permanent asset and queryable like Paimon? And it not only facilitates our data migration, but also become an asset of our data lake. And this is exactly the approach we have taken. And this is the whole pipeline that we utilized for our PostgreSQL to MySQL. Firstly, we use Flink CDC to capture the PostgreSQL's change log and sync to the Paimon append-only table. And then we transform the changelog into the executable SQL with a user-defined function and sync to another Paimon append-only table. Finally, we replay the insert, update, and create a delete function to MySQL. And everything in our pipeline is configurable, flexible, and reusable. And also, Paimon has provided an amazing functionality called branch. And whenever there's data corrupted, for example, if our user-defined function has something wrong, we can create a branch and isolate the data set and fix the data in that branch and re-ingest into our MySQL. And another functionality that we're leveraging Paimon's branch functionality is we are separating snapshot loading and incremental capture. Snapshot loading and incremental capture often have different requirements. Snapshot needs high throughput and high speed loading into the data lake as soon as possible, while incremental capture needs a perfect order. So we created the different branch for both snapshot and incremental. For snapshot loading, we ingest the data. We dramatically increase the parallelism to ingest the data as soon as possible, as far as possible, to our data lake. And for incremental capture, to keep the perfect order, we keep the parallelism to 1 and ingest it into the main branch. So this has optimized for both speed and order. And when we fall back our snapshot branch to the main branch, we'll get the full picture of the single table. And another challenge we met is PostgreSQL doesn't broadcast DDL change, and that means we can't capture our schema change in PostgreSQL. So we utilized a trigger-based pattern to help us collect the DDL to our data lake. And we basically created a trigger in PostgreSQL database. And whenever there's a table created, a record will be inserted into the table, DDL event. It contains the command, create table command, and the table name. And in this case, there is a potential race condition. We must ensure the table DDL command inserted before the actual data rows. So we apply the bucketing strategy, and we use the table name as the bucket ID for both DDL event and the table and actual data rows. In this way, we could keep the perfect order of the record for DDL and the record for the real table A. So that concludes the deep dive of our scenarios about how we work with data migration with Paimon. And next, about how we build our data warehouse and how we establish data governance, I will introduce my colleague Owen.
We use Paimon to analytics and the data migration. Now let's see how Paimon can reshape our traditional streaming ETL data pipeline using Paimon. Here is a simplified example of our data pipelines before we migrate to use the Paimon. So the first step of data pipeline is to inject the business data from various Kafka source. For example, the orders, order fleets, and order attributes topics. We first enrich the order data by joining the order fleets data in a streaming way. And we stage the joined data into an intermediate Kafka topic, which is the order detail. Then, as you might know, streaming join is a memory-intensive workload. To mitigate this issue, we write the order attributes data into an external service, which is the Apache HBase, to stage this data. This allows us to perform the lookup joins. So we can further enrich our order details by the lookup join from the HBase. And we can then sync the enriched data to the downstream warehouse for the data serving application like real-time dashboard, anomaly detection, machine learning, etc. However, this joining introduced three major challenges to us. The first challenge is the data inconsistency. Although we are using HBase to mitigate the memory issue in streaming join, however, we still need to catch the hot data in the Flink application to prevent to mitigate the network latency between the Flink application and HBase. And also we have to prevent the performance impact on the HBase server due to this frequent lookup. And the second challenge is streaming joining is a resources consuming workload. However, although we have the HBase to offload this memory intensive performance issue, but in some scenario we still need the streaming joins to ensure the data is consistent. And the third is both streaming joins and lookup joins increase the complexity of our data pipeline and slow down our data pipeline. So how Paimon can tackle these challenges? By leveraging the parcel updates, we can simplify our data pipeline. Let's take this diagram as example. We can now simply insert the data from different Kafka sources, such as the order event topics and driver event topics, into single Paimon table. And all the data will be eventually merged by the order ID. For example, the order event topics contains the order ID, the order details, and the status of the order. And the driver topics contains the order ID, status of the orders, and the driver IDs. And Paimons can merge this data by the order ID, and the null value will be overwritten by the non-null value, and the newer data will override the old data. So we can eventually get the latest value. And with this joining result, and you can see we are no longer need to stage the joined data in the Flink application. Here is the simplified data pipeline after we refactoring to Paimon. Now we can simply union all the data source from Kafka and perform the parcel update to a single Paimon table. All the data will be merged by the order ID. And the colors represent is from different sources. And for every changes, it will generate the changelog for Flink to update the data in the downstream. And you can see there's also no longer need intermediate Kafka topics and HBase for this joining. So after the refactoring, the total number of the Flink task in our data pipelines has been reduced over a half, and the CPU resources also reduced nearly 50%. Last but not least, the memory resources also reduced by 1/3. You can see this is a significant cost reduction after the refactoring to Paimon. Although while Paimon offered all these many benefits to us, we still need to ensure it is stable and performance. And data governance is one of the most important topics in data management. And when we are adopting Paimon, there's some pain points we have to tackle. The first pain point is there's no way to detect the expired consumers that should be expired. If there are any consumer that's unexpired, it will log the corresponding data and can't remove the obsolete data and lead to the storage resources waste. And the second pain point is there's no way to detect the data school in the Paimon buckets. And it will prevent us to take action as fast as possible to this scenario. And also, when we're using Paimon, there's no lineage informations can extract from Paimons, especially when we're using the password update. That's why we have implement data lakes governance to this scenario. So when we're writing data to Paimons, the Flink application will report the metrics of Paimon processes. And we can know how much data has been written to the Paimon warehouse for each commit, and how long the compaction takes. All these metrics can help us understand the performance and stability to our Paimon warehouse. However, each Flink jobs can only monitoring the table it is actively working on. So for other tables, if there's a node Flink jobs running, we will not know what's happened to that table. To tackle this issue, we should have a service to continuously monitoring this the status of Paimon warehouse, especially there's a no job running on it. And fortunately, Paimon provides a special table called the system tables. We can get the metadata from the system table. So we can set up a scheduler to periodically query this special table to get the full picture of how Paimon is currently running. And the results can report to our internal monitoring platform for alerting or to see the performance of Paimon. Let's take this special example when we are adopting Paimon. For this scenario, we found that there's actually no data school from over among the buckets. However, the compactions of some of the buckets are continuously keeping busy, and we further diagnose these scenarios, and we found that when writing smaller files into level zeros, and the level zeros files will keep merging with a large level 1 files, and the files in level 1s are not met the condition to further merge to next layers. So the large file in level 1s remains in that levels. And when we continuously writing the smaller file into level zeros, it will continuously compacting with large file. It is introducing a series of write amplifications. So that's why we have to set up the system table monitoring to for this special scenario and take action as fast as possible. And for the column level lineage, we enhance the Flink SQL parser to extract the column lineage from the partial updates Paimon table. Because we as see before, we only simply union all the data source into Paimon tables. There's no explicit join statements or where clauses. So we have to tackle this special case, and so that when there's any issue in the downstream, we can diagnose as fast as possible by tracing from the downstream back to the upstream to see what's happening to the upstream. And also when we want to change the business logic of our Flink applications, it also can analyze how the users analyze the impacts on the whole data pipeline. So this can increase the observability and the stability of our data pipeline. So in the future, we will keep exploring the ecosystem in Apache Paimon. We will investigate the Flink materials table, which can unify the stream and batch processings, and also it offers the potential to reduce the process cost in streaming. And to further optimize Paimon and observability, we will investigate the table's maintenance, which includes the adaptive compaction strategy, more efficient data lifecycle management, and also data layout optimization. Because Paimon is about writing data and manage data, we should have a service to continuously optimize the Paimon warehouse. And last but not least, we will investigate the first streaming storage because it offers more robust changelog generation. Because Paimon cannot generate the complete changelogs by this design. Because we will further and first also, as we know, build on top of Paimons, and all these are actually built on top of Paimons. So we will further improve, see how to improve the Paimon with the ecosystem. So today we share how we leverage Paimons to build, to analyze the microservice and data migrations, and also the ETL pipelines refactorings. I hope this is a valuable insights for everyone in here. Also, thank you for your time. Thank you.